Hello everyone. This is our demonstration on evaluating data trust in blockchain-based IoT systems using machine learning techniques. To start off with a brief introduction to the challenge we aim to address, blockchain technology is increasingly being integrated into a diverse range of systems, with the Internet of Things emerging as a key domain where its application is particularly significant. Blockchain has the potential to address key architectural challenges in IoT, particularly those related to centralization, data integrity, and availability. Blockchain does provide a secure and tamper-resistant environment. However, it does not guarantee the accuracy or the truthfulness of the data it stores. This inherent gap gives rise to the pervasive issue known as the bad data problem in blockchain networks. This highlights the need for reliable data trust evaluation in blockchain networks. To address this gap, we propose a novel machine learning based data trust assessment approach for blockchain systems. Here we consider both historical reputation of data sources as well as real time data trustworthiness by the introduction of a composite trust metric. Our solution uses multiple machine learning models within the blockchain framework at two different stages using edge servers and validators, ultimately functioning as a distributed ensemble for better classification accuracy. Also, our solution uses the blockchain not only for immutable data storage, but also for establishing a robust reputation management system for the data sources. In our solution approach, edge servers serve as blockchain nodes tasked with gathering sensor data from data sources and transferring it to the blockchain. At the edge server level, the data undergoes pre-processing and a binary classification is carried out using a pre-trained SVM model to classify data into trustworthy and untrustworthy categories. The SVM model calculates decision scores for each data record, indicating their proximity to the decision hyperplane, which are then scaled using a sigmoid function and combined with the historical reputation score of the data source retrieved from IPFS off-chain storage to create a composite trust metric. In the composite trust score calculation, a trust score weight denoted by lambda in this equation is introduced, which is modeled as a Gaussian curve peaking at a scale decision score of 0.5. This is to balance the effect of decision scores and reputation scores, giving a higher weight to reputation score in the SVM misclassification prone region. After that, a trust labeling is done based on a threshold using the composite trust score values. The labeled data records are stored in IPFS and the corresponding hashes are added to the blockchain. Experiments show that data points in close proximity to the decision hyperplane are often misclassified by the SVM model. Hence, those data records falling in the misclassification prone range undergo a second verification by validators implemented as Oracle services that use pre-trained machine learning models for independent analysis. Validators' evaluations are then submitted as votes, which are collected via a smart contract. The collected votes are evaluated, and based on the majority vote, the final trust labels for those data records are assigned. In case of discrepancies with the initial labels, new entries are added with the correct labels with a reference to the oldie entries. In the final step, reputation scores of the data sources are updated by considering the final trust labels of the data records. These processes are carried out by smart contract functions. In this work, the reputation score is simply set as the ratio of data deemed trustworthy by the system to the total data provided by the data source. For our demonstration, we have implemented a prototype using Hyperledger Fabric version 2.4.4, employing the Raft consensus algorithm. A client application was also implemented to interact with the smart contract backend. The programming language used was Java. For machine learning models, we used Python, and the types of models used were an SVM model at the edge server level, and KNN, MLP, and random forest as the validator level models. We used temperature data from the Intel Lab dataset publicly available on Kaggle for the experiments. Now let's look at the demonstration steps. We will first start by connecting to the IPFS. IPFS offers the same security properties as of a blockchain and is used for off-chain storage. Next, we start the Hyperledger Fabric blockchain network and run the front-end client application. Then we can use the client application to conveniently access the smart contract functions. Using them, we demonstrate data submission and processing at the edge server, data hash upload to the blockchain, and voting process by validators. Now let's watch the demonstration. Right now, we are not connected to the IPFS. Therefore, we will first make the IPFS connection. Now we can see that our connection is successful. Next, we start our Hyperledger Fabric application and the client application to interact with it. Now we have the client interface with the options for data processing at the edge server, data hash upload to blockchain, and the voting process. First, let's submit a test data file to the edge server and see the edge server output. Here we can see that it displays the SVM classification output and the classification by using the composite trust score. The test data file uploaded consists of 300 data records, and we have plotted the first 20 of them using t-SNE for dimension reduction for better visualization. The correctly classified data records are denoted in blue, while those misclassified are in red. We can see that in SVM classification, there have been 5 misclassified data records, but in composite trust score classification, it has reduced to 4. We also see the accuracies for the whole data file displayed in the CLI output, which is 70% in SVM classification and 75% in composite trust score classification. This shows that the composite trust score enhances the classification accuracy at the point of data submission at the edge server level. Now, the data file has also been uploaded to the IPFS. So we can upload the data file hash returned from the IPFS to the blockchain. Now we can see that the blockchain transaction is successful and a block containing the data file hash has been added. We can also check the IPFS to see that the data file is stored. Finally, we can execute the voting process. Here in the interface, it is sufficient to enter the data file hash, and we do not have to enter a voter ID since it is set to process multiple votes using 3 machine learning models, KNN, MLP, and random forest for demonstration purposes. Now we can see the output after voting process. The same 20 data points have been plotted, and now we see that the misclassification count has reduced to just 2. CLI output displays the accuracy, which has increased to 94% considering the final trust labels. The updated reputation score is also displayed, which was set to 0.8 initially. That brings us to the end of our demonstration. Thank you very much. If you have any queries, please forward them to rashmi.ratnaikar@uctconnect.ia.